So just a little plug for our group. We have been around since 1995, and our goal is to provide data that is useful for managers. So a lot of this climate data and resource data is useful for scientists, but we need to make it palatable for the people who are actually going to apply the data, like natural resource managers. So in an effort to help the managers in our region with climate change data, we went out and talked to stakeholders, i.e. those managers of water and climate data, and we were asking them what is most useful to them. And so we got a lot of feedback, and this is a map of the Columbia River Basin. And you've probably seen maps like this. And what we did was we downscaled a number of global climate model data and to make it useful for, or more applicable for our regional system, because as you know, these global climate models, they have a very coarse resolution. So they don't take into account the Cascades or the Rockies or the marine influence. So we downscaled these statistically to look at how those might translate into our regional climate. And then from those, we were able to provide hydroclimatic data for a number of streamflow sites. That's what these little dots are, and other data that is useful to them. So it was an iterative process with these managers, and it's ever evolving, as you can imagine. So essentially, and I'm hoping you've seen these before, but these are temperature projections from those downscaled models, and it goes from the 20th century into the 21st century. And so these are temperature projections, and these are precipitation projections. And I think Nick Bond yesterday showed you how this parses out seasonally, and we're going to get drier summers and wetter other seasons. So essentially, we feed this climate data into a hydrologic model, and what this does, it simulates the interactions between the atmosphere and the terrestrial system and it also has a snow model in it, and what we get out of that is how the hydrology in our region might respond. And essentially, the end result are these hydrologic simulations for the historical. These are 30-year time frames, so it's 1970 to 2000. For the 2020s, the 2040s, and the 2080s, using these projections into the future. So just to set the stage hydrologically in this region, we have three types of basins, and we classify those based on the dominant contributors to stream flows. So as the name implies, a rain-dominant system. So this is on this horizontal axis are the months of the year, and here the water year runs from October to September. And then along this vertical axis here is the stream flow magnitude, so the amount of water coming through that system at a given location. So the Chehalis River is a rain-dominant system, and as you can imagine, it's going to get its peak monthly stream flows when it's raining. And it's going to produce a lot of instantaneous stream flow down the river, and then it has its lowest flows in the late summer when it's not raining. Transient basin is kind of tottering between two extremes. And essentially what's happening here, like in the Yakima River, is you have two peaks, because this basin has enough elevation that a lot of the precipitation that's falling gets stored as snow in the winter. So you have a rain component here, and then in the winter you get a lot of snowpack developing, and then when it warms up, you get another peak in the summertime. And then finally, on the other end of the extreme, the Columbia River is a snow-dominant basin because its headwaters are in British Columbia, where it's quite cold. So you get most of your precipitation stored as snow, and then it warms, and you get a single peak in the late spring, early summer months. So this is a historical map, Columbia River Basin again. And what we're seeing here is these coldest basins up in the headwaters of the Columbia, and it's where you would imagine and the North Cascades, you get snow-dominant basins because it's cold enough in those regions. And then these red areas are those transient basins, the ones with the double-peaked hydrograph. And finally, in the western edges, west of the Cascades, you have more of a rain-dominant system. But as we project into the future, you can see that those maps shift. And you're going to get a retraction of these snow. This is for the 2020s, 2040s, and 2080s. You get a retraction of these snow and an expansion of these rain-dominant systems. And you can see it's even more so in the 2040s. And then by the 2080s, it looks like Washington State has no more snow-dominant basins to speak of. And this has huge implications for our water managers in the future and how, because a lot of our power is from hydropower, so how they operate their dams and how to maintain water for fish streamflow is going to be hugely important in the future, and managers need to take these sorts of projections into account. So let's just look at one of these basins, and as you all probably know, the Yakima is right in here, so it's a transient basin. And this is the historical hydrograph, the one I showed a few slides previous, and it has that double peak. But as we project into the future, you see that hydrograph shift. And that's because it's getting more of a rain contribution because of warmer temperatures and less snowpack developing, and less of a snow contribution later in the water year. And then the 2040s, that becomes even more prevalent. And by the 2080s, this hydrograph looks a lot like the Chehalis. So this, we're projecting, is going to become more of a rain-dominant system. And for agribusiness and a lot of there's huge farms around there for the irrigation purposes. I mean, you can imagine this is when they want the water to irrigate, and this is when they're having a lot less of the water to irrigate. And of course, that is due to diminishment of snowpack in our region. And so this, again, is this map of the historical situation. So this shows where our snow accumulation historically occurs. And where it's darker purple is where we get more snow accumulation. And then the lighter purple, if you remember those maps of those streamflow types, it's, if you overlay that, it's about where the transient basins exist historically. Marching into the future, the 2020s, 2040s, 2080s, we see a reduction of snowpack. So this is percent change. So the redder it gets, it means less snowpack accumulating. And so by the 2020s, we're projecting almost 20% region-wide diminishment of snowpack, about 30% in mid-century, and over 50% by the 2080s. And the basins that are most sensitive to this are those mid-elevation basins that are already on the cusp in terms of their winter temperatures. So any small bump up in temperature, they're going to have less of a snowpack accumulation, and that means that their hydrographs change, like I showed you before. So I was showing you average changes in our stream flows, but the hydrologic extremes are what gain a lot of attention for obvious reasons. This is a Chehalis in 2009. This is a salmon crossing a makeshift stream by a flooded road. And the reason we're interested in hydrologic extremes is because a lot of our engineering are built towards these, what we consider normal historical conditions, but our baseline is going to change with climate change because of that bump up in temperature. So we can't really rely on history to provide us with those normal baselines. And these systems become profoundly disturbed by these extreme events, which we think might occur more frequently. This is a little cartoon of, so you can imagine this is a river valley, like an open book, sort of a cross-section of the river valley. And this is a schematic of a cool climate flood. And so what we're seeing here is rainfall falling in the parts of the basin that are warm enough for it to rain. And then in the upper basin, you get precipitation as snow, falling as snow and accumulating as snowpack. So in a flood, in the cool season or cool climate flood, you get this amount of precipitation producing instantaneous runoff because your freezing level is sort of providing that boundary where you're going to have the rest of the precipitation accumulating as snow. But if we bump up the temperature, then that whole schematic shifts. So the freezing level goes up in elevation, and so you get a much bigger contribution to instantaneous stream flow from precipitation falling as rain rather than being accumulated as snow in the upper elevations of the basin. In the future, this is the ratio of the future to historical 100-year flood event. So the 100-year flood event is the event that has 1% probability occurring in any given year. So it's a pretty uncommon, it's not that frequent of an event, but it's something that engineers use in order to design their infrastructure. And so what we're looking at here is that ratio for the 2020s, 40s, and 80s, and where we're seeing the bubbles, these red bubbles, these are streamflow sites, where we're seeing those bubbles get bigger and redder is where we're going to have a much larger magnitude, upwards of 2 times magnitude of the 100-year flood event because of that, because we're getting less precipitation accumulating as snow. So the implications here are these, you get higher energy flows in terms of aquatic habitats, which increase erosion and sedimentation. Essentially what was historically the 100-year flood event will become more frequent if you just look at the magnitude. But if we, so yes, the magnitude of that event will become larger and the historical 100-year flood will become more frequent in the future. For aquatic habitats, in the wintertime, if we're getting more flooding, the salmon nests, known as reds, can become vulnerable to scour. So if you have those higher energy flows, a lot more water coming through your system, then a lot of these nests of the salmon that are resting during the winter and early spring will get swept downstream, and also the rearing par, or the very young small salmon that are not strong enough to withstand those high energy flows. The increased sedimentation can also suffocate those egg nests of the salmon. But there are certain actions that we can take, and we can use this data to inform managers. And this is hard to see, but it's essentially a hydrograph, but in a much smaller time scale of an urban flood. So you get these really high, flashy peaks compared to a less urbanized area, Jacobs Creek. And so the difference here is that you have a lot of impervious surfaces, a lot of a lot more concrete. So the floodplain is not, the historical floodplain no longer exists, so the water has nowhere to spread out and get absorbed by soil or vegetation. Whereas in a less urbanized area, those peaks are a lot softer because the water is allowed to spread out over the landscape and get absorbed more naturally, as opposed to these really flashy events here. So in terms of increasing the resiliency of these systems, you can maintain a complexity of these channels and allow the river to occupy its historical floodplain rather than cutting it off. On the other end of the spectrum, we're also going to see a change in the low flow regimes. So low flows are when we get the most severe consecutive, the 7Q10 is a statistic of the 7-day consecutive lowest flow that with a 10-year recurrence interval. So just think of it as extreme low flows for the future to the historical. So it's kind of the opposite here. Where these bubbles get bigger and browner is where we're going to see more severe low flows in the future. And a lot like the flooding events, we're seeing those at those mid-elevation areas because those are the basins that, because they're on the cusp, again, they're the most sensitive to the lack of snowpack or the diminishment of the snowpack in contributing to stream flows in the late summer. And so this has huge implications for salmon in terms of it reduces their rearing habitat, because salmon are a cold water species and they cannot withstand really warm temperatures or really low flows, and it cuts them off from cool refugia. It also creates migration barriers, because if there's no water, then the salmon have no way to swim upstream. So in terms of low flow, it can exacerbate the temperature impacts of the future, because this is a picture of the Klamath River in 2002. The salmon, the whole run of Chinook salmon died because it was a drought year, and if you have shallower water, then it's more exposed to sunshine, so it warms up more. And what happened here was also humans. The Bush administration overturned the protection for salmon in this particular watershed to allow agribusinesses to withdraw more water to irrigate. So this was not only a drought year, but it was also the farmers nearby were pulling out more water. It warmed up the temperatures and created the perfect conditions for a pathogen to totally wipe out this salmon run. The upside of this story is that the Klamath has now been a poster child of what happens when we take out too much water and don't account for the salmon in this system, because the tribes in this area also rely on these resources here. So looking at temperature, this is a study that we did. This is, unfortunately, we only did it for the state of Washington, but we can extrapolate out from here. This shows these continuous colors in the background are August air temperatures, and then these little dots are where we have observed stream temperature data. So this is a historical, and this is a map of the mid-century. So what we're seeing here is there is a direct relationship between air and water temperatures. So it's not a perfect relationship, but you can create a statistical relationship, which is what we did for the observed temperatures, and then we used the projected future air temperatures to see how those stream temperatures might respond. So where these colors are getting into the oranges and the reds is where it becomes very stressful for salmon, because again, they're cold water species and don't like warm water. And you can see that's hugely so for the interior Columbia Basin, where it's projected to get much, much warmer. But you also see some sites on the western side of the Cascades that are going to undergo warmer temperatures. And looking at a site on the Skagit, which is glacially fed in a pretty cold water system, we looked at future temperatures. So this is the weeks out of the year, so it goes 0 through 52. And these line graphs are the average weekly temperatures that we project. So this is, the blue is a historical, the green is 2020s, 2040s, and 2080s. And so what we're seeing here is an expansion of the duration of warmer temperatures for salmon that's beyond their threshold. These lines here show what the Department of Ecology has determined as critical rearing habitat and core salmon habitat, what they need. So this is 13 degrees Celsius and 16 degrees Celsius. And this is Granite Creek. It's a small tributary in the upper elevations of the Skagit. And if a creek like that's glacially fed is projected to undergo warmer temperatures, you can imagine that downstream that's going to become even more so. And then these bar graphs show the number of weeks that those thermal thresholds are exceeded for 13 and 16 degrees. So historically, Granite Creek had about 9 weeks out of the year that it exceeded the 13-degree threshold, but we're seeing a doubling of that by the 2080s. And historically, we saw no excess of 16 degrees, whereas we're going to see about 9 weeks out of the year. So the temperatures are not only getting warmer, but the duration of those warm temperatures is going to become longer. So this is a very simple statistical regression. So it only takes into account the change in air temperature. And because it's based on historical observed temperatures, all of those glacier inputs are sort of implicit. It's not a perfect model, but we're hoping for funding to perfect it more. So this creates a lot of thermal barriers for spawning salmon, and it reduces the habitat for the salmon that are there already, and bull trout are a huge protected species there too. So, but there are adaptation options. The drought of 2001, this is an excavated reservoir. These are the average, the 18-year average flows for the Skagit River, this brown line, and these are the observed flows during 2001. So as you can see, we're way below what, we were way below what we normally expect because we didn't get the snowpack that we expected that year. It was 52% of normal. And so because Seattle City Light has several dams upstream, they were able to help the salmon along by releasing water from the lower part of the dam, the cold water, in order to help migrating salmon make their way upstream. So my point is there are lots of adaptation options, but managers need to be informed of what to anticipate in terms of the future. And so that's why we exist, is to provide that information. I'm giving another plug to my group. But there are several groups in the region that do this sort of work and try to make this data available and applicable for these managers in order to anticipate these changes and help the salmon, help the forests along, as Dave showed in his presentation. So that's all I have for you.